Hello everyone, my name is Joseph Dwi Kristanto and I'm excited to be part of ICoSMEE 2023. Today, I have the privilege of presenting my research on the developmental shift of Preservice mathematics teachers' covariation reasoning in graphing activities. I come from the Mathematics Education Department at Sanata Dharma University in Yogyakarta, Indonesia, and I'm honored to share our findings with this esteemed community of educators and researchers. The main aim of education for sustainable development is to prepare students, including future math teachers, we'll call them PSMTs, to make informed decisions and take action in tackling urgent sustainability challenges. To achieve this, the news and mass media play a crucial role by providing information to these future math teachers about sustainability issues. For example, BBC News once reported that the global temperature has been steadily rising every year from 1850 to 2022. Such information is often presented in graphs showing changes and variations over time. That's why it's essential for PSMTs to be literate in interpreting data and graphs related to sustainability challenges available in the news and mass media. This way, they can better understand and address the pressing environmental issues we face today. Even though grasping graphical representation is crucial, a lot of students still struggle with creating and understanding graph. These difficulties at least can be classified into two types. First, some students tend to think of graphs as literal pictures of a problem instead of seeing them as abstract representations of relationships. In other words, they try to use a special coordinate systems when it's not suitable for solving the given problem. Second, students often rely on linearity even when they are supposed to graph nonlinear situations. Research has revealed that students of various ages tend to create linear patterns that pass through the origin when asked to graph nonlinear situations. For example, when plotting the growth in the height of person from birth to the age of 30, they might mistakenly choose a straight line instead of a curved one. This challenge of interpreting and constructing graph isn't limited to students, even PSMTs face similar difficulties. To develop a solid understanding of graphs, students need to grasp how graphs are created and the relationships between the changing quantities they represent. Covariation reasoning plays a crucial role as one of the fundamental building blocks for constructing and interpreting graphs. In this study, we'll explore how PSMTs develop their covariation reasoning skills when representing the relationships between two quantities that change together. To start, let's briefly describe what covariation reasoning entails in the following sections. Carson and colleagues have defined covariation reasoning as the cognitive activities involved in coordinating two varying quantities while paying attention to the ways in which they change in relation to each other. According to Thompson and Carson, covariation reasoning can be understood at different levels. No coordination level, pre-coordinations of values, gross coordinations of values level, coordinations of values level, chunky continuous covariation level, and smooth continuous covariation level. The present study aims to discuss how three PSMTs covariation reasoning develop as they represent relationships between quantities of two that vary in tandem. In this study, the case study method was employed. The subject of the study consisted of three PSMTs enrolled at a private university in Yogyakarta, Indonesia. The data used for analysis were derived from the PSMTs work in Desmos activities and video recording obtained from the Desmos teacher dashboard. To analyze the data, the researchers utilized the data analysis spiral, a method outlined by Creswell and Poth. In this study, the PSMTs participated as a single group and they engaged in discussions related to the how high is the water tag sequence, which was developed digitally using the Desmos activity builder. The digital tag sequence comprised three distinct problems preceded by a notice and wonder activity. During the notice and wonder activity, the PSMTs were encouraged to interact with an animation that depicted changes in the volume and height of water in a bottle. After observing the animation, they were asked to jot down their observations and thoughts about the context. This initial activity aimed to provide the PSMTs with a clear understanding of the context before they tackle the subsequent problems. The questions in the first two third problems were similar, focusing on the PSMTs sketching a graph to represent the relationships between the volume and height of water in a bottle. Additionally, they were required to provide explanation for their graphs. However, the three problems differed in three aspects. First, the shape of the bottle was different for each problem. Second, the presence or absence of animation showing water level and volume changes. And the third, the presence or absence of visual aids in the form of quantities representations on both axes. In the figure displayed on the left side of the screen, we can observe the graphs created by the students and their accompanying reasoning. Upon analyzing their graphs and explanations, there is no indication that the students observe individual values of water level and volume in a coordinate manner. Instead, their focus appeared to be on the overall direction of change for both variables. For instance, they noticed that as the water level increases, the volume also increases. Based on this observation, we can infer that the students are currently operating at the gross coordinations values level. In other words, they have a general understanding that the quantities values vary together, but they have not yet coordinated the specific values of the two variables in a precise manner. In the figure shown on the left side of the screen, we have the graphs generated by the students along with their accompanying explanations. Based on their graphs and reasoning, particularly in relation to the first problem, it is apparent that the Preservice mathematics teacher's covariance reasoning has reached at least the chunky continuous variation level. They demonstrated an ability to observe and identify intervals where the shapes of the bottle change, either increasing or decreasing in size. The study has demonstrated and discussed the PSMTs covariance reasoning development through group discussion in computing a digital task sequence. Although the data in the present study is limited, it can be inferred that the digital task sequence is essential in supporting the PSMTs to develop their covariance reasoning, echoing previous studies concerning the role of digital technology in covariational reasoning. Based on the study results, two principles could be considered to facilitate students in developing their covariational reasoning. First, students need to be motivated to solve the covariational reasoning tasks. Second, students need visual aids to see the relationships between the quantities being investigated, and the aids should be fed over time. The two instructional design principles could supplement some task design principles to develop students' covariance reasoning, for example, Johnson, Stephens et al. In conclusion, this study has provided valuable insight into the development of PSMTs covariance reasoning as they engage in a digital task sequence. The finding revealed that the PSMTs covariance reasoning progressed from the initial stage of gross coordinations of values to a more sophisticated levels of chunky continuous variation. Additionally, the study emphasized the significant role played by the digital task sequence in fostering the PSMTs covariance reasoning. The use of digital technology proved to be instrumental in supporting the PSMTs understanding of relationships between varying quantities. Moreover, the study proposed two important instructional design considerations to facilitate students' development of covariance reasoning. First, educators should design motivating tasks that pique students' curiosity and interest in tackling covariance reasoning problems. Second, providing visual aids can greatly aid students in comprehending the connection between the quantities under investigation. However, it is essential to gradually reduce the reliance on these aids over time to encourage deeper internalized understanding. In the end of my presentation, I'd like to share my reference list, which includes the works of inspiring researchers who have contributed to this study. Please feel free to explore this reference for further reading and insight. If you have any questions or would like to discuss any aspect of my research, I am here to listen and engage in fruitful discussion. Finally, thank you all, and I wish you continued success in your endeavors.